Hello everyone. We've seen now a number of convergence tests for series such as the divergence test, integral test, and the direct and limit comparison tests. But most of these tests assumed that the series only had positive terms. Of course, this is not always the case, and actually one very common kind of series we'll encounter later on are the alternating series, whose terms alternate between positive and negative forever, and at the moment we have pretty limited tools for dealing with those. So let's start off with a new convergence test that applies specifically to alternating series. It's called, fittingly enough, the alternating series test, and it says the following. Let sigma sum from n equals 1 to infinity of negative 1 to the power n b sub n be an alternating series where the b sub n factors represent the positive version of the terms of the series. Or in other words, the b sub n are the terms of the non-alternating version of the series. If, as a sequence, the b sub n terms are decreasing, then the alternating series converges if and only if the limit of the b sub n sequence is 0, and the alternating series diverges if the limit is anything else or does not exist. That's a bit of a mouthful, so let me try to summarize this a little more succinctly. The alternating series test says that if the terms of your alternating series are getting smaller in magnitude, then the series converges if the terms converge to 0, and diverges if the terms do not converge to 0. In a sense, you could say the alternating series test fulfills what the divergence test wants to be. The divergence test says that if the terms of a series do not converge to 0, then the series definitely diverges, but it's inconclusive if the terms do, in fact, converge to 0. The divergence test can never confirm convergence, but the alternating series test, by contrast, does let us conclude that an alternating series converges if its terms converge to 0. So why does it work? Or to get to the heart of the matter, why does it succeed where the divergence test fails? To get a handle on it, let's try to visualize the partial sums of an alternating series whose terms decrease in magnitude and converge to 0. What you're seeing right now is a plot of the partial sum sequence of an alternating series being built up term by term. Each colored dot represents a particular partial sum of the series, and each arrow represents the term that was added to the previous partial sum in order to generate the current partial sum. As you can see, the arrows alternate between pointing up and down. To help keep track of this, I colored the dots according to the direction of the arrow that points to it. A dot is colored green if it was generated by adding a positive number to the previous partial sum, and it's colored red if it was generated by adding a negative number to the previous partial sum. Another important feature to note is that although the direction of the arrows are alternating, the length of each successive arrow is shorter than the one that came before. This captures the fact that the terms of the alternating series are decreasing in magnitude as you go along. Okay, back to the question at hand. Why should this series converge? Or to put it graphically, why should the sequence of red and green dots converge to a single value? Notice another thing about this graph. The green dots are always getting lower, and the red dots are always getting higher. Why is that? Turns out, it all comes down to the shrinking nature of the arrows. Think about it for a moment. If I zoom in on a random, say, green dot, what happens as I generate the next couple of dots? Well, since it is a green dot in this case, the movement in the sequence will be downward to a red dot. After that, the movement would be upward again to another green dot. But remember that the lengths of all the arrows, red and green, are shrinking. Thus, the next upward arrow will have to be shorter than the length of the current downward arrow. Thus, the final position of the next green dot must be lower than the previous one. Of course, I made the initial dot a green dot, but the same logic works when starting with a red dot. So that explains why the green dots are going down and the red dots are going up, and that kind of suggests that they will collide. But will they? What's to stop the red and green dots from asymptotically approaching different horizontal lines, leaving a gap across the middle? The answer is the second property of the series terms. They converge to 0. That means that, in addition to shrinking, the red and green arrows must be shortening all the way down to 0 length. And since the arrows represent the distance between the green dot sequence and the red dot sequence at a particular point in the process, if the arrows shrink all the way to 0, the red and green dots must approach one another. Thus, the sequence of partial sums, represented by the dot sequence, converges, and hence the alternating series converges. Okay, time to try this out on some examples. All right, so what we're going to do is use the alternating series test to decide convergence or divergence, if possible, for the following series. So we'll start off with this one. Sigma sum n equals 1 to infinity of negative 1 to the power n divided by n. All right, so just so you can see what this thing looks like a little bit. So this is just the alternating version of the harmonic series. So if you remember, the harmonic series was 1 plus a half plus a third plus a fourth and so on. This is just the alternating version of that. All right, and if you remember, the ordinary harmonic series, where you have all pluses, is famously divergent. So now we want to find out, well, does the alternating one also divergent, or is it miraculously convergent? All right, so let's ask the AST if it is or not. All right, so what do I need to do? So the alternating series test says I look at the non-alternating version of the terms, so that would be, which I'm going to call B sub n. And so the non-alternating version of the terms is going to be just, well, 1 over n. It's the original terms of the harmonic series. All right, and then what do? We take the limit as n goes to infinity and see what we get. So if I take n to infinity, what am I going to get? Well, I'm going to get 0, of course. And because I got 0, and the original series was alternating, it turns out that this is enough, unlike the divergence test, this is enough to decide that this series is, in fact, convergent. If the non-alternating terms go to 0 in an alternating series which has decreasing sized terms, then we get convergence. The terms go to 0. Okay, pretty straightforward that one was. All right, so here's a little bit of a more complicated one. Sigma sum n equals 3 to infinity of negative 1 to the power n minus 1 times 5n squared divided by 7n squared plus n. All right, so in this case, we have negative 1 not to the n, but to the n minus 1. But the alternating series test doesn't care if you switch out which terms are positive and which ones are negative. It still works. So the usual game applies. We're going to look at the non-alternating version of the terms, which is just going to be 5n squared divided by 7n squared plus n. And then I take n to infinity in this case. So what's going to happen? Well, so in this case, we have a rational function where top and bottom have the same degree. So in that case, if I take the limit, it's just going to be the ratio of the leading coefficients, so 5 over 7. And that is certainly not equal to 0. And so in that case, the alternating series test, or really just the plain vanilla old divergence test, tells us that this series has to diverge. If the terms don't go to 0 in the limit, then whether you're alternating or not, you're going to diverge as a series. All right, moving on. Here's another one for you, which is in a similar vein. Sigma sum n equals 1 to infinity of minus 1 to the n plus 1 times n squared all over n cubed plus 4. All right, so in this case, we have a power of n plus 1, but again, the alternating series test doesn't care if you change which terms are positive and which ones are negative, just as long as it's alternating. It doesn't care which one, what the first sign is. So, take the non-alternating version b sub n, that's n squared over n cubed plus 4. And take the limit, so in this case, this is a bottom-heavy rational function. Degree on bottom is greater than the degree on top. So in that case, the limit is just going to be 0. And because this is an alternating series, the terms going to 0 in magnitude is enough for us to conclude Yep, it converges. All right, so I have one more for you guys, and I have to warn you, it's one that I think is fun. Sigma sum n equals 1 to infinity of minus 1 to the n sine squared of n divided by n. Well, okay, usual strategy, right, is we go and consider the non-alternating version, so that's going to be sine squared of n divided by n. All right, and so then we want to take the limit as n goes to infinity in this case. So what's going to happen? Well, so the trouble is we can't really do something like a L'Hopital thing, right? Because if I take n to infinity on top, we have sine squared of n, which is just going to wiggle and wiggle and wiggle forever. It's never going to settle down, so we can't actually use L'Hopital. But we don't have to use machinery that heavy, because sine squared, just like the original sine function, is bounded. And so sine squared has to forever bounce around the interval from 0 to 1, but the denominator n can grow without bound. So if the denominator is getting huge without bound, it's going to infinity, and the numerator is stuck somewhere between 0 and 1, no matter what n is, then ultimately this entire fraction has to be shrinking. Doesn't matter what the numerator is, that's just going to add some wiggling, but the overall size has to shrink because the denominator is getting huge. So this thing is going to go to 0. All right, so the b sub n's go to 0, so therefore the series converges. Right? Except that it doesn't. So, all right, so it turns out this series, or at least we can't conclude that it converges by the alternating series test. So, well, that seems weird because it looks like we did everything we were supposed to. We took the non-alternating version of the series. We took the limit as n goes to infinity and went to 0. Why on earth can't we conclude that it converges? So once again, this is the fun part. So you thought the fun part was where I was making that argument with the numerator. No, this is the fun part. So this is the fun part. What's going wrong? Why isn't this argument working, at least as far as the alternating series test is concerned? So as usual, go ahead and pause the video for a moment to ponder that and see if you can answer that. All right, so to answer this, let's take a look real quick at what the alternating series test actually says once again. So what does it say? So we have an alternating series. Okay, check, we've got that. Where the b sub n are all positive. Well, that's just by default. B sub n is just the positive version of the series, so sure. And suppose further that the sequence b sub n is decreasing. So here we are bitten by this again, I think. So if we look at our b sub n sequence, it is sine squared n over n. And sine squared n is not a decreasing function. So if I go and plot it real quick, remember sine squared looks something like this. Except this time, I'm not taking nice integer multiples of pi or fractions of pi. I'm just taking random integers and plugging it into the sine function, which is a fairly unnatural thing to do. And so what we're going to wind up getting is a sequence which looks something like this. Just going to hop around these various various humps and valleys with no particular rhyme or reason to it. So the over n is going to be dividing it, so the decreasingness might be coming from here, but it's not enough to conclude that overall this this function is going, that the overall function is decreasing. In fact, it's quite conceivable that at some point n might increase by a little bit, but then the sine function is going to jump up by a bit. So most likely there's going to be a point where the function is increasing again, and there's no reason to believe that that'll ever stop. So this is not decreasing.
So in that case, that means the alternating series test does not apply. So it's inconclusive, in other words. So note that doesn't mean that I was necessarily wrong about convergence. This thing might converge as far as we know, but the alternating series test is not going to give us, is not going to be able to confirm or deny that. It is just inconclusive. So once again, that kind of serves as another reminder to not work these problems too quickly. Always be sure that you at least keep near the front of your mind, if it's not in the very front of your mind, the assumptions of every test that we have. Because some of them, like the alternating series test, require a certain property, like the b sub n sequence needs to decrease, and if you forget that, you might wind up in a bit of a hole.
So that's the alternating series test. But similar to the integral test, the alternating series test gives us a way to estimate the remainder of a partial sum. This means, like the integral test, we can use partial sums to approximate the true sum of an alternating series and measure how good that approximation is. The remainder estimate goes as follows. If the alternating series test indicates a given alternating series, sigma sum of -1 to the n b sub n, converges, then the error, or remainder, r sub n, in using the nth partial sum to approximate the total sum of the series, is bounded in magnitude by b sub n plus 1. That is, the magnitude of the remainder is at most the magnitude of the first forsaken term, the first term that you're not adding because you're stopping the partial sum at the nth term. To understand why, let's take another look at our dot plot of an alternating series. Let's say we stop computing the series at, say, this green dot. Now consider what happens if I add one more additional term. Remember, a key feature of these plots is the green dots are going down and the red dots are going up. That means, whatever the sum of the series is, it can't be any lower than whatever the latest red dot in the sequence is. And since the green dots are going down, it means that the sum cannot be any higher than the latest green dot. Thus, whatever the sum is, it has to lie somewhere inside this gap, and the size of this gap is given by the difference between the latest green dot and the latest red dot, which is precisely the length of this red arrow, the first forsaken term. So that's the remainder estimate, and an explanation for why it works. Now, before jumping into the examples, I feel I should review something real quick, which I expect a lot of you, but not all of you, are familiar, and which you'll need for the examples, and that is factorials. The factorial of a number is denoted by placing an exclamation mark after the number, so 5 factorial would be represented like this. The way you compute it is, you multiply the number by all of the integers below it until you reach the number 1. So 5 factorial would be 5 times 4 times 3 times 2 times 1. And for a generic integer n factorial is the product of n with n minus 1 and n minus 2 all the way down to 1.
All right, so let's do an example. So let's consider the alternating series. This one right here, sigma sum n equals 1 to infinity of -1 to the n divided by square root of n plus 3. And what we're going to do is let's find out, or let's estimate, at least, the error in using the 10th partial sum to approximate the sum. So we're going to add up, so what we're imagining here is we're adding up the first 10 terms of the series, and we want to see, all right, well, how close did we get to the actual sum, or at least approximately. All right, well, the error in that approximation is also known as the remainder, or the magnitude of the remainder, so the absolute value of R10. The remainder after having added up only 10 terms. And the remainder estimate theorem tells us that this thing can be no more, cannot be any bigger than the first forsaken term. So that would be B11. All right, and so in this case, B11 is, so as a reminder, whenever I'm using b, I'm referring to the non-alternating version of the series. So this is the 11th term where I'm just going to consider the term positive, whatever it is. So that would be 1 divided by the square root of 11 plus 3, or 1 over the square root of 14. All right, and that turns out to be approximately 0.267. All right, so evidently, if we just add up 10 terms, we'll be off by the true sum by, at most, about a quarter. All right, so that's fine, although maybe that's not good enough for whatever our purpose is. So maybe we want the error to be less than that. We want a better approximation. So part 2 of the question. So how many terms do we need to add to ensure we get within, let's say, a hundredth, 0.01 of the true sum? All right, so again, we don't have any direct control over the remainder or the error, but we do know how to estimate an upper bound for the error. So in this case, I'm just going to consider the error of n. So n is just going to be how many terms I need to add up, and so r sub n is just going to be the error, and this is the thing that I want to be less than or equal to 0.01. But again, I don't have any direct tools to guarantee that. The only thing I know is that, based on the remainder theorem, this thing, whatever it is, no matter what, has to be less than or equal to the first forsaken term. So b sub n plus 1, that's the first term that I neglected in stopping the series at capital N. But this is something that I do have a lot more direct control over. And so this is the thing that I'm going to want to make less than or equal to 0.01. If I make an upper bound of the error less than the desired target, then the error, of course, must also do it. In fact, it'll do it even better. All right, so what is b sub n plus 1? Well, as a reminder, the terms of our series look like this. So, in other words, well, let me write it out over here. So my b sub n, in this case, would be the non-alternating version. So this would be 1 over the square root of n plus 3. So in this case, I'm considering b sub n plus 1. So in this case, what is this going to look like? This is going to be 1 divided by the square root of n plus 1 plus 3. Or in other words, 1 over the square root of n plus 4. And this is the thing that I want to be less than or equal to 0.01. All right, so what I'm after then is, so remember, the ultimate question is how many terms do I need to add up? Well, n is that number of terms. So if I want to answer the question, all I need to do is solve this inequality for n. That will tell me it'll tell me a condition by which I can guarantee the error is within a hundredth. All right, so I'll solve this inequality. So I think the most straightforward way to do that is I'm going to take the reciprocal of both sides. So flip the fractions on both sides. Doing that, I'm going to get square root of n plus 4 all by itself. And on the right-hand side, if I flip that, I'm going to have 1 divided by 0.01. And the reciprocal is a decreasing function. 1 over x is a decreasing function, so if I apply it to both sides of an inequality, the inequality needs to flip. All right, and so 1 divided by 0.01, that's the reciprocal of 1 over 100, so this is actually just going to be plain old 100. All right, so now let's keep on going. So I'm going to square both sides, get rid of the square root. So I'm going to have n plus 4 needs to be greater than or equal to 100 squared, which I think is 10,000. And then last step, I need to solve for n, so subtract 4 from both sides, and that's going to give me 9,996. All right, so as long as we add up more than or equal to 9,996, we should be good to go. So in that case, I'll just take the minimum. Let's not add any more than we have to. So I'm just going to say, as my final answer, take n equals 900 or 9,996, and we should be good to go. That will guarantee our error is within 1/100th. It'll probably be way better than that, but it will at least guarantee that. All right, so let's do another example in a similar vein. So example 3, let's go and approximate this series. Sigma sum n equals 1 to infinity of minus 1 to the power n plus 1 divided by 3 to the n times n factorial. And what we want to do is we want to approximate this within 0.00005, or in other words, 5 times 10 to the minus 5 of the true sum. All right, so like before, I am going to let n be the number of terms we add up, whatever it is. That's what we're trying to find out, what we need. And so what we want then is to ensure that the remainder is less than or equal to the target, less than or equal to 5 times 10 to the minus 5. That's ultimately what we want, although we can't do that directly, so we have to take a slight detour through the upper bound, which is something we actually can compute. So we know that our remainder has to be less than or equal to the first forsaken term, and that's the thing that we're going to try to force below the error threshold. All right, so let's see what we get. So b sub n plus 1, so the terms of the series, so b sub n, as a reminder, is just the terms of the series except without the alternating bit, so just imagine there's a 1 on top instead of all of this alternating stuff. So in that case, if I go and plug in n plus 1 in for every copy of n that's in here, we're going to wind up on the left-hand side having 1 over 3 to the power n plus 1 times n plus 1 as a quantity factorial. And that's the thing that we want to be less than or equal to 5 times 10 to the minus 5. Oops. All right, so like before, I think I'm going to take the reciprocal of both sides, just so the stuff that has an n in it, which I'm trying to solve for, is not in the denominator of anything. So take the reciprocal of both sides, and I'm going to get 3 to the power n plus 1 times n plus 1 factorial needs to be greater than or equal to the reciprocal of this thing, which I think, if I take the reciprocal, then 5 is going to go downstairs, and I have a negative exponent here, so if I take the reciprocal, that's just going to make it positive. So what I'm going to wind up with is 10 to the 5 on top and 5 down below. Let's see, what is that going to be? So 10 to the 5, I think that is 100,000. And we're dividing it by 5, so I think what we're going to get is that this is 20,000. All right, so maybe let me go and rewrite another line just to make it clear what we've got so far. We have this, and we want that to be greater than or equal to 20,000. All right, so if you're looking at this, you might be thinking, well, how on earth am I going to solve this for n? I guess I kind of know what to do to isolate the n over here if it was just an exponential, but whoever heard of undoing a factorial? So yeah, this is something I wouldn't recommend you try to actually solve by algebraic means, but the upshot is, I don't think we need to do that. We can actually very quickly figure out what n we need here using of all things, good old-fashioned guess and check. The reason why is because this left-hand side, what is this? This is an exponential multiplied by a factorial. Both of these are extremely fast-growing functions, so the left-hand side is going to grow extremely quickly as n increases. And so, in that case, it shouldn't take very many n's before we cross the 20,000 threshold. As far as exponentials and factorials are concerned, 20,000 is a laughably small number. So we should be able just to test a few values and see when is it that what's the first value of n that actually gets us above 20,000. Because again, the other advantage is we're not dealing with real numbers here, the n's are integers. So at some point, we have to be below 20,000, and then the next integer over crosses the boundary to over 20,000, and after that, we're good. That's all we need. Well, all right, so guess and check. Since these are such fast-growing functions, I'm just going to start pretty low. I don't know, maybe with n equals 3. Let's see what that does for us. If I do n equals 3, then I'm going to get 3 to the power 4 times 4 factorial. And I think if you work that out, what that winds up being is 1944. Not the best year, but we'll take it. All right, so n equals 3 is 1944. Well, that's not greater than 20,000. We need to find n such that we make this inequality true. So n equal 3 is certainly not the answer. Well, okay, so I guess we'd better go bigger. So maybe I'll do one more step. So n equals 4 then. In that case, plug it in. I'm going to hit 3 to the 5 power, because we have n plus 1s. 3 to the 5 times 5 factorial. Which is ultimately going to be 1944 times an extra copy of 3 times an extra 5. So this thing times 15. And turns out what you get in that case is 29,160. And now we've met our threshold. N equals 3, we were below it. N equals 4, we are above it. And certainly if we go any higher, we're just going to get exponentially, factorially bigger than that. So, yep, I think we found it. N equals 4 is the smallest value of n that will make this inequality true, and hence that inequality, and hence this one. So, yep, so I will say, so in that case, we need to add up 4 terms. So in this case, we actually want to approximate the series, so let's actually do it. Let's add up the first 4 terms of this series. So sigma sum from n equals 1, not to infinity, but just to 4 in this case. Of minus 1 to the n plus 1 divided by 3 to the n times n factorial. So that was our original series, and we're going to add up the first 4 terms, which should get us within 1 over 20,000 of the true sum. All right, so if I write it out, first term is going to be a positive, I think. And on bottom, I'm going to have 3 to the 1 times 1 factorial, so I think that's just a 1/3. Next one up, this is an alternating series, has got to be a minus. And we're going to have 1 divided by 3 squared times 2 factorial, so 9 times 2, which I guess is 18, but I'll just leave it in this form for now. It's going to get too hairy for me to compute in just a moment. All right, next one up is a plus, and we're going to have 3 to the 3 times 3 factorial. And 3 factorial, I think, is 6. 3 times 2 times 1. And one more term to go, the 4th term. 1 divided by 3 to the 4 times 4 factorial, which is 24. All right, so there we have it. And if you go and throw that into your calculator, you can approximate this as being 0.28344, just about.
All right, we've been concerned a lot lately with convergence versus divergence of a series, and we still are, but now I want to introduce you to a stronger notion of convergence, if you will. It's called absolute convergence. We say a series is absolutely convergent, or converges absolutely, if the series you get by making all of the terms positive is convergent. That is, a series is absolutely convergent if the positive term version of the series is convergent. This is a stronger notion of convergence because all absolutely convergent series are also convergent in the usual sense, but not the other way around. It is possible for a series to converge, but not converge absolutely. Such a series is called conditionally convergent, and they can have some bizarre properties. For one, it turns out if you have a conditionally convergent series, like the one below, you can change the sum of the series to whatever you want, even make it divergent, just by rearranging the order in which you add up the terms. This fact is called the Riemann series theorem, if you want to look it up. I won't go into the details of why it's true, but it again hinges on the fact that there are an infinite number of terms that you are rearranging. Another example of how weird things can get when infinity comes in the picture. So to summarize, we now have three ways in which to classify the convergent status of a series: absolute convergence, conditional convergence, and divergence.
Okay, let's get some practice then categorizing various series as either absolutely convergent, conditionally convergent, or divergent. All right, so the first series we're going to start off with is this one, sigma sum n equals 1 to infinity of minus 1 to the n divided by n squared. All right, so the basic workflow that I'm going to use is we'll first try to prove absolute convergence, because if we get absolute convergence, then we don't need to check for anything else. We're done. But if it fails, then we'll check for conditional convergence after that. All right, so let's see if this thing is absolutely convergent or not. So how does that work? Well, to check for absolute convergence, what we need to do is consider the non-alternating version of the series, or the series where all of the terms are positive. So I take the absolute value of all of the terms and I add them up. So in this case, I think that's just going to wind up being 1 over n squared. I don't need to encase that in absolute values. This thing is always positive. And then I ask, well, does this thing converge? And I think you guys know the answer. This one does converge. It is a p-series, where p is 2 in this case. So yep, this one converges. So if the positive version of the series converges, then the original series has to be what we call absolutely convergent. Ta-da! Okay, so next one up, let's revisit an old friend. Sigma sum n equals 2 in this case, although, again, that's not really relevant to the purpose, but we'll take it. So sigma sum n equals 2 to infinity of minus 1 to the n over n, so the alternating harmonic series. All right, so again, we'll ask the question, does this thing absolutely converge? If I turn all of the terms into being positive terms, then I'm going to have sigma sum of 1 over n, and this is, of course, a famously divergent series, even if you start at n equals 2. All right, so what that implies is it's not absolutely convergent. But is it conditionally convergent then? So this just shows that the positive version diverges. We haven't shown that the original series diverges. So now let's ask whether that converges or not. So, okay, so in that case, we're just going to ask, does this series by itself, as it is, converge or not? Well, okay, let's see. So this is an alternating series, so I should be able to decide whether it converges or not using the alternating series test. And so how does that work? Well, I consider, again, the positive versions of the terms, but in this case, isolated, not as part of a sigma sum, and I just ask, well, if I take the limit as n goes to infinity, do I get 0 or do I not get 0? And in this case, if I take n to infinity, I indeed get 0, which implies we get that the original series converges by the alternating series test. So this is a convergent series, which is not absolutely convergent. So in that case, it is conditionally convergent. Okay, so let's keep on going then. All right, so next one up, I've got sigma sum n equals 1 to infinity of minus 1 to the n times n squared divided by something that looks scary. So 3n squared plus the square root of n plus 1. All right, so usual game. Let's go and ask, does it absolutely converge or not? So if I convert this thing into a series with only positive terms, I'm just going to have, well, just going to get rid of the alternating piece because I think everything else is already positive by default. All right, so does this thing converge or not as a series? Well, I think not in this case by the most basic test of all, the divergence test. If I take the limit as n goes to infinity only of the terms, so if I ignore the sigma sum and I look only at the terms, if I take n to infinity, these lower order terms are not going to really matter, so I'm ultimately just going to have the ratio of the leading coefficients, which in this case is a 1 on top and a 3 on bottom. So the terms are going to converge to 1/3, which is definitely not equal to 0. So this thing, as a series, diverges by the good old divergence test. All right, but is this... all right, so the absolute version of the series diverges, but what about the original alternating version? Does it converge even though this one diverges or not? All right, well, according to the alternating series test, I need to take a look at the positive version of the terms, b sub n, which, in this case, actually turn out to be the terms we were just looking at. And what did we decide? We decided that the terms, which, again, is the same as b sub n in this case, they went to 1/3. b sub n goes to 1/3 is another way I could have said this thing. And that thing is not 0. So in that case, by the alternating series test, or indeed just by the regular divergence test, this is going to be, even the alternating version is going to diverge. So yep, it's just game over. This is a divergent series. And indeed, if you had anticipated that early on, you might have been able to see that just by applying the divergence test over here. Since the non-alternating version goes to 1/3, the alternating version must be basically devolving into you adding basically plus 1/3, minus 1/3, plus 1/3, minus 1/3 over and over and over again when n is very large. So yep, by the divergence test, good old-fashioned divergence test just on this, it's got to be divergent. All right, so let's do another one where in this case, we're going to step away from the world of regular kind of polynomial rational or rational-esque functions. Let's do something a bit different. So sigma sum of n equals 2 to infinity of minus 1 to the n minus 1 divided by n times the natural log of n. All right, so usual game. Let's consider the absolute or positive term version of the series and ask whether that converges or not. So that becomes, I guess, just 1 over n times ln of n. So does this thing converge or diverge? It's kind of hard to say. My gut instinct is always to try the divergence test first, and if I try it, just look at the terms by themselves. If I take n to infinity, then both n and ln of n are going to infinity, and so the terms are going to 0. But right now we're looking at the non-alternating version, so the terms going to 0 doesn't tell us anything. We're stuck with the divergence test, and if we get the terms go to 0, it tells us nothing. All right, so we're getting no answers out of that direction, so what else could we do? Well, one thing I note is this. So the terms here are maybe a little more complicated than we like. It has an n and an ln of n, but it's not that bad. In fact, I think we've seen stuff that looks like this before in the semester in the context of integrals. So I think what I'm going to try next is the old integral test. So let me convert this thing into an integral. So this would be the integral from 2 to infinity of 1 divided by x times the natural log of x dx. And let's ask whether that converges or not. Okay, so what I'm going to do here, then I think I need to do a u sub, right? So I have ln of x, and its derivative is 1 over x, which conveniently shows up right there. So I think that's a good choice. I'm going to do u is ln of x, du is 1 over x dx. And let's see what we get. So I think I'm just going to end up with the integral of 1 over u du, and I need to adjust the bounds. So in this case, I'm going to do something that is, I guess you're technically not supposed to do, but if you know what you're doing, it turns out to be okay. I'm going to just treat infinity as if it was a number. And so I can avoid doing all the variable stuff and taking limits in this case. All right, so in that case, I'm just going to plug in 2 and infinity into ln, which is my u function, in order to convert the bounds. So the lower bound becomes ln of 2, and the upper bound becomes ln of infinity, but that's also infinity in the limit anyway. Okay, so we're left with this, and if I integrate 1 over u du, I'm just going to get ln of absolute value of u, but I think the bounds are both positive in this case, so I don't think I need to worry about that. So I'll just write it as ln of u, evaluated from ln of 2 to infinity. All right, so if I plug those in, I'm going to get ln of infinity, which is infinity, minus the version where I plug in ln of 2, so that is ln of ln2, which is a weird number, but it is finite, whatever it is. So infinity minus something finite is also infinite. All right, so in that case, that tells us that this thing has to diverge. All right, so the positive version of the series diverged. All right, so that means it's not absolutely convergent, whatever else it is. So now the question is it fully and finally divergent, or is it conditionally convergent? Okay, well, to answer that, we'll consider the b sub n terms in isolation. This is an alternating series, so to apply the alternating series test, I consider b sub n, which is just 1 over n times ln of n, and I ask, does this thing converge to 0 or not? Well, I think we already answered that early on when I attempted to apply the divergence test. This thing converges to 0. But since we're in the context of looking at an alternating series, the fact that the terms go to 0 is enough for us to conclude that, yes, the original alternating series converges. And since we already eliminated absolute convergence, it has to converge conditionally. All right, so I've saved the best for last, as I always do. Best is a relative term. All right, sigma sum, n equals 1 to infinity of cosine of n divided by n to the power 3 over 2, 3 halves. All right, so usual drill. We'll consider the absolute positive term version of the series to see if we can establish absolute convergence or not. So the absolute version of this, so this is cosine, not cosine squared. It's plain vanilla cosine, so it can give you negative numbers, but not in a predictable way, because we're just plugging in n and not n pi or anything. So in this case, I don't think I can avoid writing absolute values, so, oh, okay. Absolute value of cosine of n. But I don't think I need them on the bottom. N to the 3 over 2 is always positive, so no need to write them down there. All right, so the question is, well, does this thing converge or not? All right, well, we have a cosine going on, which is making things pretty complicated. I certainly wouldn't want to integrate that. I'm not even sure if I could. But I don't think we have to. If we have some annoying thing present in the function, a good trick to get rid of it in the context of deciding convergence or divergence is to make use of one of the comparison tests to see if we can somehow just replace the complicated cosine in this case with something that is simple that we would like. So what I would really like is to compare this thing against just 1 divided by n to the 3 over 2, because that would just be a p series, and that would be really easy. So can I do that? I think yes. So remember, cosine, right? Just ignore the absolute values for now. Maybe let's look at this one. Cosine, its range is between -1 and 1. If I take the absolute value, the range is going to change to be between 0 and 1. It's as if I've squared it, although it looks a little different if you graph it. But the range is the same. This thing in absolute values has to be stuck between 0 and 1, whatever it's doing. So in that case, if it's stuck between 0 and 1, then in particular, it has to be smaller than 1, cosine does. So I can get a bigger series if I write this as sigma sum n equals 1 to infinity of 1 divided by n to the 3 over 2. All right, and so in this case, now I have the p series that I wanted. So in this case, 3 over 2, so my p is 3 over 2, that is bigger than 1, which means this is going to converge. All right, so does that tell me anything? What happened here? So it converges, in other words, this thing is finite. So I've shown that this series, which I'm currently interested in, is less than or equal to something finite. So therefore, this thing must also be finite. So this thing converges by the direct comparison test. All right, so we have that the absolute version of the series converges. And so what that means then is we're done. The absolute version of the series converges, which is hard to do, or harder to do than the original. So in that case, this original function, or this original series rather, has to converge absolutely. So now, of course, there's probably other ways that you could do this. You might be able to do a limit comparison on this one as well. I'm not sure. But in this case, I think I like what we did. So we used the direct comparison test, which is a less powerful tool. But in this case, I think it made things a bit simpler. I could eliminate the cosine immediately, and I just happened, by chance it seems, to have gotten a favorable inequality. So yeah, this might be a good example of why it's still good to keep direct comparison in your mind, even though limit comparison is, in a lot of ways, a better test. But it's not as fast or as simple of a test.
Okay, I have one last test to go over with you today, and it's a big one. It's called the ratio test, and it is a very good test for determining absolute convergence of a series. I would ask that you try to pay special close attention to this one, because we'll be making use of it a lot, almost exclusively, when we get to power series. It says, given a series, sigma sum of a sub n, take the limit of the absolute value of the ratio a sub n plus 1 over a sub n, and if the limit you get is strictly less than 1, then the series is guaranteed to be absolutely convergent. If the limit is strictly greater than 1, then the series is definitely divergent. But if the limit is exactly equal to 1, or does not exist, the ratio test is inconclusive, and you'll need to use a different test. A good thing to keep in mind about the ratio test is it works particularly well on series whose terms involve factorials or exponentials. As for why it works, I won't give a detailed explanation today, but you can kind of understand how it works by thinking about what the limit of that ratio represents intuitively. The limit represents what the ratio of a sub n plus 1 over a sub n approximately equals for large values of n. If that ratio is less than 1, then it's essentially saying that, for large values of n, the series resembles a geometric series whose r value is less than 1, and hence convergent. But if that ratio is greater than 1, then for large values of n, the series resembles a geometric series whose r value is greater than 1, and hence divergent.
All right, so like before, we're going to try to determine whether the following series converge absolutely, conditionally, or diverge. But this time, we're going to use the ratio test as much as possible to decide that for us. All right, so the first series I've got for you guys is sigma sum n equals 1 to infinity of minus 5 to the n divided by n times 7 to the n plus 1. All right, so the ratio test says that we consider the absolute value of the ratio a sub n plus 1 over a sub n, so the ratio of the next term to the current term in absolute value, and we take the limit of that and see what we get. Well, all right, so let's see what this thing is first of all. So the way I usually like to write these things down is I first just go and write down a sub n plus 1. I don't worry about any fraction stuff. Just write down a sub n plus 1. So that'll just be the terms of the series where I replace every n with n plus 1. So I'm going to have minus 5 to the n plus 1, and I'm going to divide by n plus 1 times 7 to the n plus 1 plus 1, so that's going to be n plus 2. Add 1 to every copy of n. All right, so that's a sub n plus 1. Now I need to divide it by a sub n. That is the original vanilla formula for the terms. But instead of dividing a fraction by a fraction, what I'm going to do instead is I'm just going to multiply by the reciprocal flip of the original formula. So that's just going to give me n times 7 to the n plus 1 divided by minus 5 to the n. All right, and the task is to take the limit of this as n goes to infinity and see what we get. But let's not get ahead of ourselves. I think we can make the problem a lot simpler before we start throwing limits at this thing. So a lot of stuff here I think cancels, right? So we have a minus 5 to the n and a minus 5 to the n plus 1. So in that case, the exponents can subtract from each other. So this minus 5 to the n is just going to completely go away and just going to get rid of that n on top. It'll just leave the 1. What else? So I think over here we also have something going on. We have 7 to the n plus 1 on top, and we have 7 to the n plus 2 on bottom. And so they will almost all cancel, just like these did. 7 to the n plus 1 is just going to completely cancel away. And all but one copy of the 7 over here is going to cancel away. All right, so what does that leave us with? So it's going to have absolute value of, I guess, negative 5 times n on top, divided by, I guess, just n plus 1 times 7. All right, so I have a negative going on there, but this is an absolute value, so why don't I just drop the negative? And I think if I drop that negative, then I think all the other terms here are all positive, right? So in that case, if I just drop that negative, I no longer need absolute value bars, which is rather nice. All right, now let me go and distribute the 7. 5n divided by 7n plus 7. All right, so now I think we're in a much better position to start talking about limits. So if I take n to infinity here, this is a rational function where the top and bottom are equally heavy, as it were. So if I take the limit as n goes to infinity, I'm going to get the ratio of the leading coefficients, which is 5/7. All right, so what does that tell us? So the critical thing about 5/7 is it is a number that is less than 1. And so according to the ratio test, if you take the limit of this thing as n goes to infinity, I guess I should have said that. Take the limit as n goes to infinity, and you get something, anything, that is less than 1. Then the original series you started with is absolutely convergent, hands down. It's not just convergent, we can go ahead and declare it is absolutely convergent. All right, so not so bad. Though I'd like to get done a number more examples. And again, I want to emphasize that the ratio test is actually, in this class at least, a very, very important convergence test, maybe the most important one. So definitely make sure that you get used to this and how this works. We're going to be using it almost exclusively in a week or so. Okay, so next one up, we have sigma sum of n equals 1 to infinity of, in this case, n factorial divided by 6 to the 2n plus 1. Okay, so ratio test says, what do? I take the absolute value of the next term divided by the current term. So in this case, so I think all of the terms are already positive. So you know what? I don't think I even need to write an absolute value bar anymore. All right, so n plus 1, that's going to be n plus 1 factorial, divided by 6 to the power 2 times n plus 1 plus 1. Okay, and so then I need to multiply by the reciprocal of the original. So that is 6 to the 2n plus 1 divided by plain vanilla n factorial. All right, so let's simplify this down a little bit. So what am I going to get? Well, first thing, let me clean this thing up. That looks very ugly. Let me go ahead and condense the fractions also. Don't have too many fractions floating around. All right, so let's condense this. So that's going to be 6 to the power 2n plus 2 plus 1. If I distribute the 2, and 2 plus 1 is 3. So evidently, this just collapses into 2n plus 3. Which kind of makes sense. There's a 2 in front of the n, so if I increment n by 1, then the overall exponent should increase by 2. All right, so now let's go and do the cancellation part of this. All right, so let's deal with the exponents first. That's something that's rather familiar. All right, so as far as the exponents go, I have 2n plus 3 downstairs, and I have 2n plus 1 upstairs, so everything upstairs is going to be eaten up by all but, I think, 2 copies of 6 downstairs. So we're going to have just 6 squared as the only thing surviving down below. Now, what about these? Can I simplify factorials? So, well, let's think about it for a second. So what is the definition of a factorial? So the idea is you start at whatever number is listed there, and you just multiply by all of the numbers, you multiply it by all of the numbers that are below it all the way down to 1. So n plus 1 factorial can be written as n plus 1 times n minus 1 times n minus 2, and then so on all the way down to like 2 times 1. And very similar thing with n factorial. N factorial breaks apart into n times n minus 1 times n minus 2, and all the way down to 2 times 1. And so written out explicitly like this, I think you can see all of the cancellations that are going to happen. N cancels with n minus 1 cancels with n minus 1, and so on. And so indeed, all that we're left with is just going to be a single n plus 1 on top, and just 6 squared down below. In essence, what we've really done, just to kind of reemphasize this trick so you don't have to write this out over and over every time. Another way you can see this is n plus 1 factorial can be written as, well, n plus 1 times all of the stuff that's below it, but all of the stuff that's below it multiplied together is n factorial. So in that case, if I have this thing divided by n factorial, it just collapses into n plus 1. All right, but however you think about it, we wind up here. And I think that's something now that we can handle taking a limit of. So if I take n to infinity, what's going to happen? Well, the numerator is just going to grow without bound. The denominator is just going to scale it down by a constant factor, but it's not going to stop the inflation by any means. So this thing is going to diverge to infinity. And of course, infinity is certainly greater than 1. So by the ratio test then, that tells us that the original series has to diverge. If we get something greater than 1, then hands down diverges. It doesn't even converge conditionally. It's just game over, diverges. All right, so now it's time for a little more interesting one. Blech. I have sigma sum n equals 1 to infinity of negative 1 to the n times n squared times 8 to the power n minus 1 all over 3n plus 1 factorial. All right, so what does ratio test say? It says I need to take the limit of this ratio. So what is it going to be in this case? I think I have enough room. So let me write it in. All right, so in this case, I'm going to have -1 to the n, but again, so -1 to anything, it's either going to be plus or minus 1. I'm taking an absolute value anyway, so I think I'm just going to ignore it. All right, so just ignoring that, I'm going to have, for my n plus 1, I'm going to have n plus 1 squared times 8 to the power, I think it's just going to be n. And down below, this is going to be 3 times n plus 1. So the coefficient of 3 in front of the n means that if I increase n by 1, it's going to cause a change by 3 to the total expression. So this is going to become 3n plus 4 factorial. And now I just multiply by the reciprocal of the original. So that's just going to be 3n plus 1 factorial divided by n squared times 8 to the n minus 1. Again, ignoring the -1 to the n because I'm taking an absolute value anyway. All right, so let's see if we can clean this up a little bit. So again, I think now that we've gotten rid of the -1 to the n, everything else is strictly positive, so I don't think there's any need to write down an absolute value anymore. So let's see what cancels with what. So I don't think I can do anything with the polynomial pieces. 8 to the n, okay, that'll cancel with, or cancel partially with this. So this is 8 to the n, 8 to the n minus 1. So all of these are going to cancel away with all but one surviving copy of 8 up above. What about these factorials? So this one is a little bit trickier to see. So let me go a little slowly with that one and write out what we've write it out more explicitly. So for now, let me go ahead and update what we've got. So we still have n plus 1 squared, except now we have times 8, and we have times 3n plus 1 factorial. And down below, let me put the n squared on the left-hand side this time, and we have 3n plus 4 factorial. All right, so I think we all kind of have a vague sense that this should kind of cancel with that, but it's not entirely clear how, perhaps. Can I just do what I did before and just cancel that one away and get rid of the factorial there? Is that going to work or not? Well, okay, so let's go back to the drawing board real quick and write out what these things really mean. Well, first of all, let me note one thing. 3n plus 4 factorial is probably, well, it is. It's got to be bigger than 3n plus 1, right? 3n plus 1 factorial. Because here I'm taking the factorial of something bigger. So in that case, let me go and try to break this one apart into smaller pieces and see if I can get it to correspond with that. So I'm just going to copy the numerator real quick. And what's going to happen downstairs, let me just write down the product, the factorial as a product. So that's going to be 3n plus 4 times the next one down, which is going to be 3n plus 3, times the next one down, which is 3n plus 2, and then maybe one more times 3n plus 1. Aha! I've actually gotten down to where I started over here. But what's going to happen after 3n plus 1? Well, I'm just going to multiply by the next one down, 3n, and then so on. In other words, I'm just going to have 3n plus 1 factorial here. 3n plus 1 times n times blah, 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 which is exactly what this thing is doing. 3n plus 1 times 3n times blah, blah, blah. So indeed, that's how I can go and cancel these out. So it doesn't cancel, this thing doesn't cancel and just leave one term behind. It actually leaves 3 terms behind. All right, so let's see what we get when all of the dust settles. So I think I'm going to move the 8 over here. So I have 8 times n plus 1 squared divided by n squared times 3n plus 4 times 3n plus 3 times 3n plus 2. All right, and we are tasked with taking the limit as n goes to infinity. So this looks a little bit painful, but remember, if you recognize the structure of this, this is a rational function, polynomial over polynomial. And if you take the limit of a rational function, you remember that the only things that matter are the leading terms. So in that case, I don't need to actually expand all of this out, which is what you might be afraid of. All I really need to do is just keep track of whatever the expansion is, what is the leading term going to look like? and that's not too hard to do. So looking downstairs, well, actually, now that I come to think of it, I don't think I even need that. Because I think the degree on bottom is going to be larger than the degree on top, right? So on top we have a quadratic, that's degree 2. And on bottom we have linear times linear times linear, so all three of these together is a degree 3. And then I have another n squared, another quadratic. So I have a quadratic times 3 linears. That's going to be a degree 5. So this is going to be a top-heavy, or I'm sorry, a bottom-heavy rational function. And if I take the limit as n goes to infinity, it doesn't even matter what the terms are. This thing has got to go to 0. And, of course, 0 is less than 1. So the ratio test then guarantees that we have absolute convergence of the original series. Okay, so I have one last example for you guys. All right, so sigma sum n equals 1 to infinity of, in this case, negative 1 to the n times n plus 2 divided by n plus 1 cubed. All right, so we're in a ratio test frame of mind. So let's go ahead and try it out. So I'm going to take the ratio of a sub n plus 1 over a sub n. So what am I going to get in this case? All right, so in this case, I'm taking an absolute value. So I'm just going to ignore the negative 1 to the n. It's just plus or minus 1, so it's just going to not matter in the absolute value. So n plus 1, plug it in for n. I think I'm going to wind up having n plus 3 on top, and on bottom I'm going to have n plus 2, that quantity cubed. All right, then multiply by the reciprocal of the original. So that's going to be n plus 1 cubed divided by n plus 2. All right, what does that simplify into? Well, it doesn't look like it really simplifies into much. I mean, I guess I can condense the fractions, but that's pretty much it. I guess I can also drop the absolute values, right? Because all of this is... Well, yeah, because all of this is going to be positive for large values of n. Yep. All right, so we have this going on. So this is another rational function, right? We have polynomial on top and polynomial on bottom. So in that case, we know how to handle it. We're hoping that we won't need to expand all of this out. Maybe we won't if the degrees are imbalanced. So what's the degree on top going to be? So this is a cubic times a linear. So on top, we're going to have a degree 4. And on bottom, we've got a cubic times a linear, which is also degree 4. Well, okay, that's disappointing. That means it's equally heavy on top and bottom, which means I actually need to do the work and find out what the leading coefficients are. Well, okay. I mean, that's not actually that bad. If I just care about the leading coefficients, then I don't need to expand all of this out. And it's actually not too hard to anticipate what the leading coefficients of these things are. So it looks like I might have to expand this cubic, but I don't really have to. So... but if I was to do it, what it would look like is I would have, as my leading term, right, I would have n times n times n as part of my triple distribution, so I would have n cubed. But that would be the highest order term. There would be a whole bunch of other stuff which wouldn't matter in this case, so I'll just write that off as a plus dot dot dot. And same thing down below, I think. N plus 2 quantity cubed is just going to leave me with n cubed plus a bunch of garbage. All right, well, continuing in this fashion, if I was to imagine distributing all of this through, what would be the highest order term I would get? That would come from multiplying first with first in the process of foiling, as it were. So that would just give me n to the 4th on top, plus a whole bunch of lower order terms that I don't care about. And the exact same thing happens on bottom. I have n to the 4th plus a whole bunch of stuff I don't care about. All right, so if I take the limit then, as n goes to infinity, what I'm going to get is the ratio of the leading coefficients, which are both 1 in this case. And so I get that the limit is 1. And what does that tell me? I think that tells me nothing, right? Yeah, because the ratio test, right, says that if you take the limit of a sub n plus 1 over a sub n, and you get something that is exactly equal to 1, then you learn nothing. The ratio test throws up its hands and says, I don't know, do another test. All right, so we're inconclusive at this point, but I don't think we want to let that stop us. So in that case, let's see if we can determine whether this thing, the original series, converges or diverges using another test. All right, so in that case, we'll get out of the mindset of the ratio test. The ratio test is useless. So let's just go back to the drawing board and look at this thing for a moment. Well, okay, so this is an alternating series. And so ultimately I want to decide, does it converge or diverge? And if it converges, does it do so absolutely or conditionally? So let's just turn this into kind of one of the examples we saw a little while ago. And let's try to see if it's absolutely convergent. So in that case, I would consider the positive version of this series, or the positive term version of the series, which in this case I think just amounts to getting rid of the negative 1 to the n. So I'd have sigma sum of n plus 2 divided by n plus 1 quantity cubed. All right, and so I'm asking the question then, does this series converge or diverge? Well, it's not entirely clear, although this is a rational formula, right? So it bears some resemblance, perhaps, especially for large values of n. The plus 2 and the plus 1 are going to stop mattering. And so in the long term, this looks like it's going to resemble n over n cubed. All right, which turns out to be 1 over n squared. And so as a p-series, if I was to sigma sum that, we would know it would converge. So let's see, can we use the direct comparison test to do that? Because that's nice, quick, and simple. So in that case, if I'm trying to prove convergence, then I would want to show that this formula is smaller than this formula. Can I do that? Well, so what did I do to get this formula? I got rid of the plus 2, which made the numerator smaller. Okay, so, and I think then we already have a problem, don't we? So I shrank the numerator, which shrinks the fraction, and so that's not what I want to do. All right, so it looks like direct comparison is not going to work. But limit comparison should work, right? So if I take a look at this using the limit comparison test, what do I need to do? So this is my a sub n, and I'm going to call this my b sub n. And so limit comparison test tells me I need to take the ratio of a sub n over b sub n, which in this case I guess will be n plus 2 divided by n plus 1 cubed, as my a sub n, and then I divide by this thing, which is the same as multiplying by the reciprocal, so multiply by n squared, and see what we get. So if I multiply the n squared through, I'm going to get, I think, n cubed on top plus 2n squared, and on bottom, if I was to pretend to expand it out, I would have n cubed plus a bunch of lower order garbage. All right, and so now limit comparison test says I need to take the limit of whatever this thing is as n goes to infinity. And if I do, both top and bottom have the same degree, so it's just going to be the ratio of the coefficients. And so I take the limit, I am going to get 1 yet again. But in the context of limit comparison, that actually does tell us information, because 1 is a number that is between 0 and infinity. And so what that tells us then is the original series we had, sigma sum a sub n, and sigma sum b sub n have to have the same convergent status. And sigma sum b sub n, what was that? That sigma sum n equals 1 to infinity of 1 over n squared. That is a convergent p-series. So in that case, by the limit comparison test, the original series also has to be convergent. But if you remember the sigma sum a sub n, this thing which I'm calling the original series isn't actually the original series, This one was. This was the positive version of the actual series whose convergence I was interested in. So what have I shown? I've shown that the positive term version of the series is convergent by the limit comparison test. So that means that the true original series has got to be absolutely convergent.